challenge and context, physical principles related to smart grids. In this video, we'll talk about common principles and concepts of smart grids. At the end of this video, you will be able to describe the different power quality factors, describe how voltage and frequency variations influence our power supply. Power quality can be described as the absence of any problem in the power grid that could result in a failure or misoperation of customer equipment. Continuity of service and power supply at every instant of time is essential for all power quality issues. Moreover, voltage and frequency quality play an important role while evaluating power quality. Modern equipment has become more sensitive to voltage disturbances, and frequency deviations lead to unstable power grids. Voltage quality regulations aim at keeping the voltage in its ideal sinusoidal waveform. Deviations might provoke equipment damages and hence have to be prevented. The typical sinusoidal waveform of the voltage V over time t is depicted in this diagram. Voltage quality requires this curve not to be affected by load changes. It has to keep a sinusoidal wave shape with constant amplitude and a constant time period, also expressed in terms of the frequency f. Important for the customer and directly linked to the maximum amplitude is the root mean square value, also known as RMS. Voltage quality requires a constant RMS value, as this is the voltage value delivered and promised to the customer. As our electrical grid is operated with 3 phases, in order to fulfill the voltage quality restriction, these phases have to be symmetrical at all times. A symmetric 3-phase system is depicted in the diagram. European Regulation EN 50160 determines the voltage characteristics for power distribution systems. Voltage quality is mostly important to prevent equipment damages. Frequency quality, on the other side, ensures the stability of the power grid and prevents power outages and blackouts. The frequency depends on the level of generation and consumption. If the amount of power generation in the grid equals the amount of consumption, frequency in Europe yields the desired value of 50 Hz. If the generation exceeds consumption, the frequency increases. If the consumption exceeds generation, the frequency becomes lower than 50 Hz. Grid operators are responsible to keep the power grid stable in order to ensure the equilibrium between generation and consumption for every instant of time, and consequently keep the frequency at 50 Hz. In Europe, transmission grid is interconnected between the countries, and actions to ensure constant frequency can be adjusted accordingly. If a frequency deviation occurs, a proper adjustment mechanism has to be employed to restore the grid balance. There are 3 control options that are activated one after another until the value 50 Hz is reached. Primary control measures activate generation units that can start within seconds and have to be able to supply their full amount of power 30 seconds after activation. Secondary control replaces the primary control over the time period of minutes and has to be completely activated after 5 minutes. Next, tertiary control would replace secondary control by rescheduling generation. It operates during the time period of 15 minutes. If the frequency is not reaching 50 Hz after these measures are taken, grid operators will start to disconnect large consumers to recover to 50 Hz. The last step to prevent a blackout and ensure the power supply would be splitting up the European grid into small subgrids, which will then try to reach the equilibrium separately. To summarize, voltage and frequency are vital power quality elements that ensure the continuity of service, and hence the power quality of our electrical grid. Mitigation of frequency deviations implies triggering or disabling power sources according to their response time. Primary control is triggered in seconds. Secondary control is triggered in minutes. Tertiary control is activated under a quarter of an hour. Thanks for watching.